Hey, everybody. So I wanted to basically take a few minutes to tell you a little bit about deriving probability distributions. And this is basically a recap, or maybe it's a redux, of the lecture I presented today in class. But then I'm also going to go through a number of examples at the end to hopefully cement some of these concepts. So with that, let's get going. Okay, so remember, this was the situation we were trying to address. We essentially have a random variable x for which we maybe have a probability distribution, either a PMF or a PDF. We also have a random variable y that we would like to calculate a probability distribution for, given a functional relationship between the random variables y and x, given here by little g. And so really the question that we're trying to answer is, how do we derive the probability distribution for the random variable y, given a probability distribution for the random variable x and a functional relationship between the random variables x and y? And that may seem kind of hypothetical and theoretical, but in fact, there's a lot of really cool problems that this theory enables you to address, as you'll see in a bit. Here's an example that we went through in class. Well, most of these slides are from in class anyway. We basically are going to focus for the first example on a PMF. So imagine that we have a PMF for the random variable x shown here. And so we have a series of xi's for which there are, let me turn on my little laser pointer. So we have a series of xi's for which there are finite probabilities indicated by the green balls. And what we'd like to do is derive from this PMF for the random variable x a new PMF for the random variable y. So we don't know where these balls are going to be located or necessarily what their probability will be. We want to derive a function for that, given a functional relationship between the random variables y and x given by g here. And then, of course, we can also write the random variable x as the inverse function of y. And so we both have the relationship between y as a function of x, g of x, as well as x as a function of the inverse of g operated on y. And the main point that I wanted to make was that if you think about it, say that this event here has a 10% probability of occurring. So in 100 trials, we're going to get maybe 10 of these events occurring on average. If this event occurred 10 times out of 100 trials, then we would expect that whatever the corresponding event was over here in the y domain would also occur 10 times, right? Because essentially this functional relationship is taking that event that occurred 10 times in x and translating it into an occurrence in y 10 times. So we in general would expect that for these PMFs that the probability that x is equal to some specific value of xi is going to be essentially equal to the probability that y, the random variable y, is equal to corresponding yi value. And so really the issue is, how do we relate xi and yi? And of course, we can relate them directly through the functional relationship given here, xi equals g inverse of yi. And so if we kind of run with that concept, we basically say that the probability that the random variable y will equal yi is equal to the probability that x equals the corresponding xi, which is given by g inverse of yi. And so the kind of conclusion is that for PMFs, it's actually pretty straightforward to derive a PMF from a known PMF, say derive this PMF for the random variable y from the PMF of the random variable x by just simply substituting for x the g inverse of yi. So that's kind of the strategy that we're going to use for deriving PMFs. And let's do a quick example. So we're given this information. We're given that the PMF for the random variable x. And so basically you can see there are 3 possible events for the random variable x. It could equal 1, 2, and 3. And the probabilities associated with those events are 0.25, 0.5, and 0.25. So that's the PMF for the random variable x. We're also given a functional relationship between a new random variable y and this old random variable x. Basically that y is equal to x squared, and we're also restricting ourselves to x, the random variable x, being greater than or equal to 0, which will become important in just a second. What we'd like to do is derive the PMF for y, so we want to kind of fill in this blank spot here. And we recognize that basically from this functional relationship, we know that yi is going to be equal to xi squared, where again, xi is greater than or equal to 0. So basically for every event in x here, we expect there will be a corresponding event in y that is related to that xi through this quadratic formula. And so, for example, we can imagine that an event random variable x equal to 1 is going to map to the random variable y equals 1, because 1 squared is equal to 1. Likewise, the random variable x equal to 2 is going to map to the random variable y equal to 4, because x squared in this case, 2 squared is 4. And likewise, 3 maps to 9. And so, so we know that the location of these 3 events, how they map from xi to yi. Now we want to determine what the probability would be at each of these sort of events in y. And of course, we have this relationship which says that the probability of each of those events in y are just going to be equal to the probability in x of the corresponding xi's, which are given by this G inverse of yi. And so that's fairly straightforward, because we know G inverse here in this case is just positive square root yi. Notice we don't have the plus or minus here because we're restricting ourselves to positive values of xi. And so that means that in order to sort of determine the probability at each position here, we just simply run with this formula. We set the probability that y is going to be equal to 1, for example, equal to the probability of x equal to square root of 1, which of course is just 1. And so that means we can map the probability here of 0.25 over to this position in yi space. And likewise, we can do the same thing here. Basically, in this case, we've got 4 is the yi, so our random variable y is equal to 4. We take the square root of that, we get 2. So we map the probability at xi equal to 2 to the probability at yi equal to 4. And likewise, for this event x equal to 3, it just maps to y equal to 9 with the same probability. And so, I don't know what that extra, oh, that's the laser pointer. I'm like, what is that extra point there? Oops. And so this is our answer, right? So we've just now derived our first PMF, given a PMF in for the random variable x and the functional relationship between y and x. Let's do another example. I think we did this pretty quickly in class. Example 4.1 in the book. So consider a cantilever beam with a length L that is subjected to a concentrated load F applied at the free end of the beam. So you got a beam, it's tied to a wall here, and we've got a concentrated force at the end of the beam. Suppose that that load or that force consists of a number of boxes, each of the same weight of 1 unit. The number of boxes loaded on the beam x varies from 0 to n and is distributed as a binomial distribution in which the probability of a box being loaded is p. This means that the load F has a binomial PMF as follows. So that's our PMF that we're given for the load or the force that's applied to the end of the beam. And basically, it's given in terms of the number of boxes that are loaded on the end of the beam, given n, and the total number of boxes that could ever be loaded, and the probability that you're going to get a box loaded. And so what we're asked to do is find the PMF for the bending moment, where the bending moment is going to be equal to that concentrated force times the length of the beam. And so in this case, it's a pretty straightforward problem. We want to find P of M. So that's what we're deriving, is the probability distribution for that random variable M. And in this case, the inverse function is just going to be F equals to M over L. And we substitute that in for X. And so we're just going to get P of m is equal to the same exact PMF except x. Everywhere you see an x, you replace that x by m over L. And we did that in class. Sorry, I don't have the visual on it, but I think you can, it's simple enough that you can see what happened there. All right, so now let's think about a CDF now, and we're really talking in this set of slides, or really this particular lecture, we're focusing on the case where we only have a function of a single random variable. So in the next lecture, we'll talk about what happens when we're talking about a function of say, joint random variables, and it could be two or more. So it gets a little bit more complicated. But for the time being, we're just going to focus on a single random variable. And so now we're asked to derive the CDF associated with a derived PMF or PDF. And basically here, we basically start with the definition of a CDF, which is we want to know for the derived distribution what the probability is that y, the random variable y, is less than or equal to some specific value, little y. And so that's what we're kind of after. And if we think about it, we know that every y maps back to the probability that x is equal to the inverse, the g inverse of y. That was from our previous result. And so we would expect that the CDF would basically either have one of two forms. There would be one of two inequalities here, and we need to figure out which one it applies. Either it would be the probability that x is less than or equal to the inverse g of y, or it would be that x is greater than the inverse of g operated on y. And as it turns out, and I'll explain why in a second, basically the top case applies if g of x is an increasing function of x, whereas the bottom case applies if g of x is a decreasing function of x. And let me kind of go through each of those examples and explain graphically what I mean. So here's a situation where the function g of x is an increasing function of x. So you can see g of x is plotted on the vertical axis, x is plotted on the horizontal axis, and indeed g is increasing as a function of x in this particular case. And so suppose that we are interested in the probability that the random variable y is less than or equal to a specific value of that random variable little y. And so I'm denoting that little specific little y value by this horizontal line here, intersecting the y-axis, the vertical axis at this point. And we are specifically interested in the probability associated with values of the random variable that are equal to y or smaller. So we're really interested in this range of y values, maybe going off to negative infinity. Now we can then think about what the corresponding values or range of the x coordinate would be. So x is just going to be g inverse of y. So that's basically the vertical line here. So that's the location of the specific realization for the random variable x that corresponds to the specific realization here for the random variable y. And the point that I want to make is that if we're interested in random variable y being less than or equal to little y, that's going to basically correspond to realizations of the random variable x being less than or equal to g inverse of y. In other words, as you move down in y, you're going to be following this curve down, and it's going to move to the left and then to smaller random variable or smaller x values. And so that is why when g of x is an increasing function of x, the probability that y, the random variable y, is less than or equal to little y is equal to the probability that the random variable x is less than or equal to the inverse, g inverse of y. Now let's consider the opposite, or the other possibility, that we have decreasing g of x as a decreasing function of x. So I've given an example here where, again, on the vertical axis, we're plotting g of x, and you can see it's declining with increasing x. And we're, again, interested in this probability that the random variable is going to be less than or equal to a specific value of y, which is denoted here by the horizontal lines. So we're interested in this region here, that y is less than or equal to little y. And in this case, the inverse function, of course, is going to give us this vertical bar here, this location for the random variable x equal to a specific value of x, little x, which is equal to g inverse of y. And if we follow that curve down for declining values of y, we can see what's going to happen is that basically we're going to be looking at the x, random variable x, being greater than g inverse of y. In other words, the realizations in x are going to move to the right as the realizations in y move down. Oops, sorry. So in that case, I'm sorry, it's a little bit offset. The probability that the random variable y is less than or equal to little y is going to be equal to the probability that the random variable x is larger than g inverse of y. And that again applies if g of x is a decreasing function of x. So here's kind of the summary. Then we've got our two different choices for the probability of the random variable y is less than or equal to y, depending on if g of x is an increasing function of x or if g of x is a decreasing function of x. That's fine. But remember, these are just the definitions of the CDF. So we can write then the CDF for y in terms of the CDF for x. And also this case here. So we basically have two choices of the CDF for x, depending on whether g of x is an increasing function of x or g of x is a decreasing function of x. And how do those look? So basically, I've just kind of used the definition of the cumulative distribution function. So remember that is equal to the probability that y is less than or equal to y. So that's going to be my CDF for the random variable y, evaluated at little y. And that's going to be equal to the CDF for x, evaluated at g inverse of y, provided that g of x is an increasing function of x. Or it's going to be the complement of this, so it's going to be 1 minus the CDF for x evaluated at g inverse of y. Again, if g of x is a decreasing function of x. So those are kind of our derived CDFs, and so how we relate it to how we relate the derived CDF of y to the derived CDF of x, depending on whether g of x is an increasing or decreasing function of x. So now what we'd like to do, kind of the crown jewel here, is we'd like to be able to derive the corresponding PDF for y. So we've derived the CDF for y, and of course the CDF and the PDF are related through differentiation. And so, so the strategy here is to express the CDF of y, and then essentially take the derivative of it and use the fundamental theorem of calculus. And so I've just rewritten what that would look like in the case where g is an increasing function of x. Again, we've got our CDF evaluate for y, evaluated at little y, is going to be the CDF for x evaluated at g inverse of y. And by definition, this is going to be equal to the integral from minus infinity to the upper limit g inverse of y of our PDF for x, f of x of u du, where u is just the dummy variable. So here's the trick. What we do to recover the relationship between the PDF for y and the PDF for x is we take the derivative of both sides of this equation with respect to y. So we know from definition that the PDF for the random variable y is just going to be the derivative with respect to y of the CDF for y. And if we take the derivative with respect to y of this right-hand side here, this integral, basically what we're going to get is we're going to get the we're going to get the argument here of the integral, which is fx, evaluated at the upper limit, which is g inverse of y, times, and this is through the chain rule, the derivative of g inverse of y with respect to y. So we're essentially just applying the chain rule. We're taking the derivative of the integral first and evaluating that derivative relative to the upper limit, so using the fundamental theorem of calculus. And then we're taking that times the derivative of that upper limit, g inverse of y, with respect to y. And this result that the PDF for y is just equal to the PDF for x evaluated at g inverse of y times the derivative of g inverse of y with respect to y is going to be valid only in the case where the derivative with respect to y of g inverse of y is greater than 0, which is exactly the same thing as saying that g is an increasing function of x. And I have a little picture to show that. So here's a case, again, where we've got g as an increasing function of x. So g of x is plotted on the vertical axis, x is plotted on the horizontal axis, and you can see it's clearly increasing. We've got a specific value of y, the corresponding specific value of little x. It's just going to be the g inverse of y. And you can see as as we increase this x value, or in other words, we increase g inverse of y, we're going to necessarily increase y because the curve is moving upwards. And that means that the slope, the derivative of g inverse of y dy, is going to be greater than 0 in this case. So this statement, this inequality, is essentially equivalent to saying that g of x is an increasing function of x. And let's look at what happens if g is a decreasing function of x. We basically go through the same rigmarole, but it's a little bit different because now the CDF for the random variable y evaluated at little y is going to be 1 minus the CDF for x, random variable x evaluated at g inverse of y. Remember where this comes from? Basically, this comes from, kind of go back a bit. So it basically comes from the fact that the probability that the random variable y is going to be less than or equal to little y, that's the definition of the CDF of y, is equal to the probability that x is greater than g inverse of y if g of x is a decreasing function of x. So of course, we can write this as the complement of the CDF for x evaluated at g inverse of y. And so that's all I'm doing here is I'm basically just substituting for this case, g being a decreasing function of x, I'm equating the CDF for y evaluated little y to 1 minus the CDF for x evaluated at g inverse of y. And by definition, the CDF for x evaluated at g inverse of y is just minus the integral from minus infinity to g inverse of y of f of x, the PDF for x, integrated with respect to the dummy variable u in this case. And so I play the same game. I basically, to recover the PDF for y, I take the derivative of both sides of that equation. So we know that the PDF for the random variable y is just going to be the derivative of the CDF for the random variable y, which in this case, if we take it over to the right-hand side, the derivative of 1, of course, is 0. And then we're left with minus the derivative of this integral, which is just going to be the integrand evaluated at g inverse of y times, that's what we've got here, times the derivative of g inverse of y with respect to y, again, applying the chain rule. And so you notice what we've got here is we've got this minus sign sitting out in front, which we didn't see before. But we also note that in this case, that is, g is a decreasing function of x, this derivative dg inverse of y dy is going to be less than 0. And I've got a little graphic to show that. So this is a case where g of x is a decreasing function of x. You see it's going down. And we've evaluated, or we're looking at a specific value of y. And then, of course, the corresponding specific value of x is just going to be g inverse of y. And we can see what's going to happen here is that in the case where g inverse of y increases, so we're moving to the right along the x-axis, that's going to necessarily lead to a decline in y as we move down that curve. And so in this case, the slope is negative, or dg inverse of y is less than 0, which is exactly the same thing as saying that g of x is a decreasing function of x. So coming back, that's why we have this inequality here, dg inverse of y dy is less than 0. And I guess the main point here is that in this particular case, where g is a decreasing function of x, we have a negative sign out in front of the PDF for x, and we also know that dg inverse y of dy is negative as well. And of course, two negative signs multiplied together cancel, so this overall quantity is going to be positive. And that's nice because it means that whether the function g of x is increasing or decreasing with x, we can write out the PDF for y in terms of PDF for x in terms of this sort of universal result here, at least for single-valued random variables or random variable functions. So basically what we've done is we've replaced the dg inverse of y dy that we had before with the same thing, but now we've got absolute values. So that takes care of both the increasing and g of x increasing and g of x decreasing with x. And it's the overall quantity is positive. So this is our master formula that you must know for calculating PDFs for the random variable y, given the PDF for the random variable x, and the functional relationship between x and y is denoted by g here. So let's do some examples to kind of hopefully cement these ideas. So this is example 4.2 from the book. And basically it says, consider the PDF of the normal variate. So we're given kind of the normal distribution here for a PDF of x. Should look very familiar by now. And this is a two parameters PDF, remember? So we've got the parameter mu x, which is the mean, and parameter sigma x, which is the standard deviation. So anyway, that's the PDF of x. And now we're asked to derive a new PDF for the standard normal variate s, which is related to x through the following formula. And of course, you all recognize this as being basically the way that we would transform a normal problem involving a normally distributed random variable into the standard normal, and then we'd go from there to calculate probabilities, for example. And we know how this works out, but it's interesting to apply our formula and just make sure that it works, right? So, and if you think about it, this is exactly the kind of problem that our formula was designed for, because we're asking for the PDF of a new random variable called big S, that's the standard normal, as a function of the random normal distribution, or the random variable for x, which we know is normally distributed. So we know the PDF for x, we'd like to know the PDF for s, and we know the sort of formula that relates the two. So this is absolutely the kind of problem that this theory was designed to solve. So the goal is then to derive a PDF for s. And we begin step one by calculating the inverse function, because we need that. We know in our formula. And in this case, we can solve for the inverse function. Basically involves solving for x in terms of s. That's what G inverse would give us. And so x is equal to G inverse of s is just going to be equal to sigma x times s plus mu x. So this is our inverse function. Step two is to calculate the derivative of the inverse function with respect to s in this case, which when we do, mu x, of course, is constant. And so the derivative of G inverse of s with respect to s is just going to give us sigma x here. And then we remember our formula, step three, which basically says that new PDF for the random variable s is going to be equal to the old PDF for the random variable x evaluated at G inverse of s times the absolute value of the derivative of G inverse of s with respect to s. We know this quantity here, the derivative, is just, is just equal to sigma x, right? And we know that this quantity here is just going to be the sort of normal distribution for x, but evaluated instead of at x at G inverse of s. So let's kind of run with that. So this is, again, our formula here. I'm just reproducing it, but now we're going to substitute. So basically the derivative G inverse of s ds is going to be sigma x is equal to sigma x. So that's where that sigma x comes from. And then the fx is going to be our PDF for x. But now instead of evaluating it x, we're going to evaluate it at G inverse of s. And remember, G inverse of s, let's just go back a second, is equal to sigma xs plus mu x. So keep in mind that plus mu x, because when we substitute it in here, the plus mu x is going to cancel with the minus mu x, so that's going to leave sigma xs. And of course, the sigma x in the denominator is going to cancel with the sigma x in the numerator, and we're going to be left with s. So when we're all said and done, these two sigmas cancel. The sigma in the numerator and denominator cancel, the mu's cancel, and so we're left with this very simple form of the normal distribution, which we immediately recognize is the standard normal distribution. So it has a zero mean and a unit standard deviation. So basically, we've now proved what we knew before, which is that when you perform that variable transformation, kind of going back here, where you let the standard normal variate equal to the normal variate minus the mean divided by the standard deviation, you end up with a normal PDF with zero mean and unit standard deviation. But so I guess you could say, hey, we knew that already. Why is that interesting? It's just basically showing that our formula gives us what we know has to be correct. So it's just kind of a test of the formula. Okay, so that's example 4.2. Now let's kind of move on with another example, a little bit along the same lines, example 4.3, and this involves the log normal distribution. And so we're going to basically derive a result that we kind of already knew. But it's, again, nice to see that our formula works. So the problem setup is as follows. Suppose a random variable x has a log normal distributions with parameters lambda and zeta. In that case, the PDF of that random variable x is going to be equal to fx of x is equal to, essentially, it looks like the normal distribution, remember, but there's really two fundamental differences. One, there's an x in the denominator here. Well, there's a couple fundamental differences. We've got the x in the denominator. We also have a zeta instead of a sigma, okay? And also, instead of x, we've got natural log x in the exponent here, as well as lambda and zeta playing the role of the mean and the standard deviation. And remember, the notation for this particular PDF is ln capital N, meaning log normal of the random variable x given lambda and zeta. Okay, so that's all just definitions. That's the definition of the log normal distribution. You've seen that many times. We are then asked to derive a new PDF of the function y equals to natural log x, given that the random variable x is given or follows this log normal distribution. So we know what the PDF for the random variable x is. We know what the functional relationship is between y, the random variable y, and the random variable x. What we're asked to do is then, from that information, derive the PDF for y. And, you know, before we even go anywhere, you can probably figure out what's going to happen. This is essentially a new random variable that is the log transform of the original random variable. And so if the original random variable is log normally distributed, if we take the log of those values, basically then y should be normally distributed. So that's kind of what we're trying to show here. All right, so we run through the same set of steps. So step one, we calculate the inverse function. If this is the function g of x, then the inverse function is just going to be solving for x there in terms of y, which is going to give us x is equal to e to the y, or g inverse of y is equal to e to the y. Then we can calculate the derivative of the inverse function. So we just take the derivative of this function here. And of course, the derivative of e to the y with respect to y is just e to the y. So I'm just kind of coming up here. So basically, then we substitute these results in step 3 into our PDF, or our new formula, I should say. And so our formula for the PDF of the random variable y is going to be equal to the PDF for the random variable x, evaluated at g inverse of y, times that derivative of g inverse of y dy. Well, we know this quantity here is just e to the y. See, we showed that here. So we can substitute that one in. And if we take our log normal distribution and substitute g inverse of y, remember what g inverse of y is, it's just e to the y. So basically, this is going to be the PDF for x, where the random variable x is set equal to g inverse of y, which is e to the y. And you can see what's going to happen here is if I substitute e to the y in for the argument of the natural log of e to the y is just y. And then we've got e to the y down here, which is going to ultimately cancel with that e to the y there. And so when we carry out that little bit of algebra, lo and behold, we now end up with the PDF for the random variable y, which you will recognize as the normal distribution for the random variable y. But the standard deviation in this case is zeta, and the mean is lambda. So the right way to say that is that after that transformation, we're talking about a normal distribution of the log transform random variables given lambda and zeta. So in fact, our expectation that the log normal distribution for the random variable x is equivalent to the normal distribution of the log transform random variable x, or random variable y, has been validated by our formula. Okay, so that's all fine and good. We talked about how to think about these problems if g of x is a increasing function of x or a decreasing function of x. What if it does both? It increases a bit and then decreases a bit, such that the inverse function, g inverse of y, doesn't have a unique or a single value. So let me explain what I mean by that. So Again, suppose that our random variable y is equal to some specific value, little y, which of course corresponds to this horizontal line here. And you can see that horizontal line crosses the curve for g of x at two locations. So there's not a single value of x that solves that, that equation. There's actually two roots. There's going to be the root over here and the root over here. And that's a case where the x equal to g inverse of y is not unique. There's multiple, in this case two, but there could be, you know, lots of different roots to this equation in such a situation where we have portions of the curve, the g of x curve, that are rising and falling. And so in words, basically, we were saying that in an event of the random variable y, that would be the specific value of little y here, random variable y equal to little y, now corresponds potentially to multiple events for the random variable x. So we've got multiple random variable x events corresponding to a single event for the random variable y. And that becomes an issue if we're trying to map, you know, the probabilities from the random variable x to the random variable y, right? So how do we handle this? Well, basically, mathematically, the answer is that we just think about this single event, that the random variable y equals little y, as the union of all possible roots ranging from 1 to k, in the last case k was 2, of the random variable x being equal to those roots xi. So that's the way to think of it. And again, k is going to be the number of roots of the equation g of x of y. What is a root of this equation? Basically, you're saying that if I define the value of y, say I give it a value like 2 or something, then I'm going to have multiple x values which satisfy this equation. Those are all roots of that equation. If x is a discrete random variable, then these unions of events just work out to being sums of probabilities, of course. And so in that case, the probability that the random variable y is equal to little y is just going to be the sum over all the roots of the probability that the random variable x is equal to g inverse of y for each of those particular roots. So xi equal to gi inverse of y is just the ith root of that equation, gx equal to y. Likewise, if x is a continuous random variable, so this would be like the PDF version of the result we just described. So the PDF of y is going to be our same formula that we had before. The PDF for the random variable y equal to some little y is going to be, you know, it looks very similar. We've got the PDF for the random variable x evaluated at g inverse of y times the derivative of that g inverse of y dy. But now we're summing over all the roots for that solution xi equal to g inverse of y, summing them over all k roots, where again xi equal to g inverse of y is just the ith root of that equation, g of x equals y. So this becomes our master formula then when we are interested in deriving a PDF for y given a PDF for x and a situation where we have multiple roots for this equation, g of x equal to y. And so here's kind of the big summary. Again, in the case where g inverse of y is not single valued, we're going to say that the event random variable y equal to little y is going to be the union of all of the events associated with those different roots for x. And then if we have a discrete random variable, that is essentially just the sum of the probabilities associated with each of those roots translated into the probability for random variable y equal to y. Likewise, if we have a continuous random variable, then it's just going to be our formula that we derived earlier for calculating the PDF for the random variable y, but now summed over all of those different potential roots. Okay, so let's do a couple of examples. I mean, this all, again, seems very theoretical, but then when you start applying it, you realize how it works. And I think you'll have that experience too as you work through some of the problems. Okay, so here's example 4.4. The strain energy in a linearly elastic bar subjected to an axial force S, it's a random variable, is given by the equation So this is the strain energy, U, is equal to the length of the bar divided by 2 times the cross-sectional area of the bar times the elastic modulus, or modulus elasticity of the material. So these are basically just a set of constants times the axial force S squared. And because these the L over 2AE are just a collection of constants that are going to be, specific to the particular problem of interest, particular bar length and particular cross-sectional area and modulus of elasticity, we might as well just call them by one constant, just lump them together and call that constant C. So really we're talking about the strain energy being equal to some constant times the axial force squared. So it's a quadratic relationship between the two of them. And we're going to assume that the axial force S is a log normal variate with parameters lambda and zeta, and we're asked to derive the PDF for the strain energy. So that's the goal. We want to derive a new PDF for U given a PDF for S that's specifically the log normal PDF and this functional relationship between U and S. So as before, the first step is that we calculate the inverse function. So we essentially solve for S in terms of U. And so when we do that, now we aren't restricted, like, previously we had a problem like this and we were restricted to, say, S greater than 1. We're not restricted to that in this case. And so the general inverse function is going to be essentially plus or minus square root U over C. And so you can see that there are two roots in this case that solve that equation, G of U equal to S. One of them is a positive square root U over C, and the other one is a minus square root U over C. So we have two roots that we have to track. Step 2 is we calculate the derivative of the inverse function. We're going to take the absolute value of it, so we don't really care about the plus or minus anymore. And when we do that, we just basically end up with a 1/2, and then of course U to the minus 1/2. The C is also in the denominator square root C, so just kind of changing up the notation here. And if you simplify that, that becomes 1 over 2 square root UC. So, so that's our derivative of the inverse function with respect to U. So, so then if we come back to our formula for multiple roots, remember we basically need to take that derivative with respect to of G inverse with respect to U, substitute it in, and then we're going to have a sum over these various roots. And we only have two roots, right? S equal to plus or minus square root U over C. And so that means that in this case, F of U, remember that's going to be the strain energy. The PDF for the strain energy is going to be equal to the PDF for the applied axial force S. So that's the axial force evaluated at the two roots, which are just the G inverse of U there. And one of them is a positive square root U over C, and the other one's a minus square root U over C. And then this derivative of G inverse of U with respect to U is just the 1 over 2 square root UC that I've indicated here. Now, so we've got these two different PDFs that we need to evaluate here in terms of the axial force. Make sure that's right. Yeah, axial force S. And remember that Fs is a log normal variate, which is confined to values of the random variable greater than or equal to 0. And so this Fs evaluated at minus square root U over C, that's going to be the random variable in that case is less than 0. And so that means that this quantity here has to be 0 because, again, the log normal variate doesn't exist for negative values of the argument. And so basically we can drop this term out. And so what we're left with is this is our expression for the PDF for the random variable U in terms of the PDF for the random variable S. And recall, Fs is a log normal variate, which means we can write it out. And we're specifically interested in the one positive root, which I'm indicating here as S1. So you can see S1 is right here. And then I've just written out the log normal distribution, or PDF. So remember, you got zeta for the standing in for the standard deviation. We've got our S1 because that's going to be in the denominator for the log normal. And then we have log of S1 minus lambda, the log of the median, and divided by zeta. And then we just multiply by the 1/2 square root UC, because that's our derivative of the G inverse with respect to U. And our one root that we're considering is square root U over C. So we substitute those in and do a little bit of rearranging. And we finally end up with this relationship here for the derived PDF of U in terms of zeta and that constant C, which is, again, a sort of a lumped constant consisting of other terms. One of the things that's interesting to do is compare this new derived PDF to log normal distribution. And what we'd realize is that this quantity here is acting like a new mean, and our new sort of standard deviation of the log transform values is 2 zeta. And you can see 2 zeta appearing in the denominator here too. So in fact, our derived distribution, that is the random variable, the PDF for the random variable U, is just a log normal variate, just like the original one was, but with new parameter values. So lambda of U is equal to natural log C plus 2 lambda, right? Instead of it being equal to lambda, it's equal to natural log C plus 2 lambda, and zeta of U is now equal to 2 zeta. So that's kind of a cool result. Okay, let's do another example. So basically it's the same as the last example, but in this case, the applied force random variable S is a standard normal variate with PDF and 0, 1. So that's just the definition of the standard normal, 0 mean unit standard deviation. And we're asked to derive the PDF of the strain energy. So that would be F of U in this case, where instead of a log normal distribution for the applied force, we have a standard normal variate distribution for the applied force. And recall where we got to, the point where we had to actually evaluate the PDF for S was this result here. Everything else is the same up to this result, where we're basically saying that the PDF for U is going to be the sum of these two different PDFs, one evaluated as square root UC, U over C, the other one evaluated negative of that, times, and this was the derivative of G inverse derivative of G inverse with respect to U. And in this case, the F of S is going to be the standard normal variate. And when we substitute that in, basically what we're going to find is we end up with this result here. And now if Fs is the standard normal variate, remember one of the really key things about the standard normal distribution is that it's symmetrical about 0. So that means that this function, evaluated as square root U over C, is going to be exactly equal to this function evaluated in minus square root U over C. So we might as well just write it as a single square root function evaluated at square root U over C times 2, but then there's also 2 in the denominator, so those two cancel. So we end up with this quantity here. I just moved the square root UC, went over the square root UC out to the front, which is why it's sitting here. And so then we finally substitute the standard normal PDF for F of S, and we end up with an extra square root 2 pi and the e to the minus U over 2c, because we're now putting square root U over c for S squared there. Interestingly enough, this particular distribution, so this is our solution in that case, this particular distribution, and I'm showing on the next page, is actually called the chi-squared distribution with 1 degree of freedom. And so here I'm plotting that PDF for the random variable U against U, and that's again a chi-squared distribution. Okay, let's do another example. This is kind of a cool example and certainly relevant to what we've been hearing about with some of the dams overflowing with all the rainstorms we've been having in California. So this is example 4.6. The overall height of earth dams must have sufficient freeboard above the maximum reservoir level in order to prevent waves from washing over the top of the dam. Remember, if it's an earthen dam, basically it's just made of earth, right? It's not cement. And so if the the water in the dam starts washing over the top of the earthen dam, what will happen is it'll erode that sediment and the dam will fail. So this is a really serious issue. You definitely do not want the water in the dam to go over the top of the reservoir. So anyway, the determination of the overall height that you have to have that top of the dam above the sort of maximum reservoir level. Also, I mean, it has to include what's called a wind tide and wave height. So basically, a wind tide is when the wind's blowing over the surface of the reservoir, so that body of water, it's going to kind of push water to one side, and then it's also going to generate waves. And so basically, that pushing of the water to one side creates the tide, right? So the water kind of comes up at one side, maybe drops and comes up and drops. But then on top of that, you have surface waves that arise because of that that wind. So if you've ever been out on a boat during a windy day, you know that that you get a lot of surface winds and a lot of chop, a lot of sea associated with that. So anyway, there's this empirical relationship for determining the overall height that the dam has to be that factors in the wind tide and the wave height. And basically that overall height Z, which is going to be the wind tide essentially in feet above the still water line. So this is the elevation that you're going to have, your dam is going to have to be at least this high to deal with the wind tide, is equal to the fetch, which is essentially the length of the reservoir over which the wind can blow and kind of push the water, and divided by 1,400 times the depth of the reservoir over the fetch, times v squared, where v is the wind velocity. And so just like that other example, we recognize that the fetch over 1,400 times the depth is essentially a constant, which would be a characteristic of a particular dam design. So we can just lump that into the constant little a here. And so then what we have is that the wind tide height, that's the height above the still water line that our dam better go to, otherwise it's going to overtop, is equal to that constant a times the wind velocity squared. And so here's the cool part. So basically, we're asked to derive the PDF for the wind tide. That's, again, the probability density function for those sort of water levels we have to design for, assuming that the wind speed, v, is exponentially distributed with the mean velocity of v naught. And so the exponential distribution, of course, looks like this. Remember, the PDF has to have units of inverse v, which whatever those are. And so v naught is appearing in the denominator here. And then our argument is just minus v, which is the wind velocity, the specific realization of the wind velocity, little v, divided by that characteristic wind velocity v naught. And so the way to read this is that this is the PDF for the random variable for wind velocity, big V, evaluated as a specific wind velocity, little v, and given the characteristic wind velocity v naught. So we have this PDF for the random variable of wind velocity v. We're asked to derive then the corresponding PDF for that that height that our dam has to go to sort of handle all possible sort of wind tides. And so basically in this case, as with the previous two problems, we have two roots for the inverse function g inverse. So if we go back to this functional relationship between z and v, it's basically z equals av squared. And so when we take the inverse, that's going to be v is equal to z over a, and then the square root of that. And of course, we'll have a plus and minus out here. So we've got two roots for the g inverse of z, and that's going to be plus or minus z over a. We can then take the derivative of g inverse of z with respect to z, and that's going to just give us, because this is z to the half, so we're going to end up with the z to the minus 1/2 or that square root z in the denominator there. And after a little bit of algebra, this is what that quantity there works out to. And remember, we take the absolute value, so we don't have to worry about the plus or minus in front of the inverse function here. So we have the inverse function, plus or minus square root z over a. We've got that derivative of the inverse function with respect to z. is just 1 over 2 times square root a z. And we also know what the probability density function is for the wind velocity. It's just that exponential PDF. And so we've got everything that we need to calculate a PDF or derive a PDF for the random variable z. Remember, that's just going to be equal to the sum over the roots, and we have 2 roots. And basically where our G inverse is going to be evaluated, those 2 roots. And when we carry that out, so we're going to have 2 terms in the sum. This is going to be the case where we evaluate the PDF for the wind velocity at the positive root for G inverse, which is square root z over a. And then we have plus the PDF for v evaluated at the negative root. And then this derivative of G inverse with respect to z is just 1 over 2 times square root az, which you can see right here. Again, the exponential distribution is confined to random variables that are greater than or equal to 0. So we can immediately exclude the second root and just drop it out, which is nice. And so we're left with that the PDF for the random variable z is just going to be the PDF for the random variable v evaluated at square root z over a, and then that times 1 over 2 square root az. And when we plug all that in and plug and chug and simplify, we end up with this final probability density function for the wind tide that we have to design for, given the functional relationship we described before, plus the PDF for the wind velocity. So that's pretty cool. And that's all I have for you today. And so basically continue reading Ang and Tang. And on Wednesday, we will talk about how this theory is modified in the case where you have functions of multiple random variables, not just a single random variable. Okay, and so with that, I will turn off the screen share if I can figure out how to do that. It's always a challenge. Yeah, and I'll say goodbye. Thanks for listening.